Hello students, I am Dr. Gajendra Purohit and you are watching my channel where I upload videos on engineering, mathematics and B.Sc. If you are preparing for any exam that involves higher mathematics, then my YouTube channel is very helpful for you. You can watch previous videos of Discrete Mathematics on the I tab. Today, I am going to explain hash diagrams and concept of lattice, that which will be the hash diagram and if it will be lattice. We will also discuss concepts like maximal elements, minimal elements, greatest lower bound and least upper bound in the hash diagrams. So please watch this video. So what is a hash diagram? A hash diagram is a graphical representation of a partial order relation in which all the arrowheads are understood to be pointing upwards. It simply means all the relations we have here are partial order relations. And they will keep relation with the upper points. It means that the arrow diagrams will be made in upward direction. Getting it, right? Let's try to understand this with an example that what we want to say. So I will try to explain it. Let's take an example and try to understand this hash diagram. Imagine we have a set containing number 1, 2, 3, 4, 6, 8. What are we seeing here? So it is written as B ordered by the relation. A is divided by B here. It says that A divides B, right? So how will we take its relation? We have to define its relationship. So what will be the relation? Here you can see that we will write all those which are divided by number 1. So 1 divides 1. 1 divides 2. After that 1 divides 3. 1 divides 4. 1 divides 6. And here 1 divides 8. That will be the relation here. Okay, now after number 1. Let's talk about number 2 here. We have 2 divides 2. What after that? 2 divides 4. Then we will write 2 divides 6. Finally, 2 divides 8. Now let's talk about 3. Here 3 divides 3. The relation here is based on conditions and whatever relation we have should be a partial order relation, right? 3 divides 3 and when we talk about next, 4 divides 4. And 4 divides 8, right? Then we talk about 6. So students, 6 divides 6 and it doesn't divide anything else. 8 divides 8, right? So we have this relationship. Now you have been told that this should be a partial order relationship, right? If this is a partial order relation, then we have 3 conditions. One is reflexive, meaning it is going on its own. Second is antisymmetric. It means that if 2 is going on 6, then 6 should not go on 2, right? For example, if 2 goes on 4, then 4 should not go on 2. That's what antisymmetry means, right? So we know that this is antisymmetry and transitive. Transitive means that if we have a relationship like 1 is going on 2 and 2 is going on 4, then there must also be a 1 and a 4. So as here it is 1 and 4, so it is showing transitive property too. This is a partial order relation. Whenever we draw a hash diagram, it should have a partial order relation. It means that it should be reflexive, antisymmetric, and it should be transitive, which it is. Now let's understand how to draw a hash diagram. So what we do is we bring this thing here, right? So one can divide which of these, right? So here students, you can see that. It is dividing 2. 1 here is dividing 3, right? It is dividing itself as well, right? Actually, I'll write it like this. It's better if I don't draw the arrow. Here 1 is dividing 2 and dividing 3, right? Now students, you can see that 1 is dividing 4, right? And 1 is also dividing 6 here. Correct or not? Students, 1 is also dividing 8. So we can write it like this. Now after this students, let's talk about 2, right? Here we can see that 2 is dividing 4. 2 is dividing 6 and 2 is dividing 8. Clear? Now let's discuss 3. So students, 3 is dividing which of these? 3 is dividing 6 and itself. Also, each number is dividing itself. This is understood. No need to write it like that. That these are dividing themselves, is this clear? Now let's talk about number 4. So I will use a different color to show 4. So 4 is dividing 4 and students 4 is also dividing 8 here. You can write it like this. Now let's talk about 6. 6 divides itself, 6 is dividing 6 and 8 is dividing 8. Now my dear students, I want to tell you that to create a hash diagram, we need a partial order relation. First property of a partial order relation is that it is reflexive. An element should go over its own, meaning it divide itself. When it's in the definition, there's no need to show it with an arrow. So we won't represent those who are going over their own. We have no need for it. It's in the definition. We won't do it from here because it's ultimately part of its definition. So we don't need to explain it here. We'll erase it here. So we have removed it now. Let's talk about the second thing, that is antisymmetry. Antisymmetry because we have a graph that's going upwards. It's not that 1 is dividing 2, so 2 will also divide 1. Whenever we have a relation here, it's defined from bottom to top, not top to bottom, right? And that is already happening in this. So when we are placing an element above another element, then relation is not coming opposite or inverse, right? We need to pay attention to this. This is the biggest thing in a hash diagram. What's the next property? It's transitive. The transitive property means that if 1 is dividing 3 and 3 is dividing 6, then 1 will divide 6. We don't need this line. It simply means that this line which you can see here, students, we don't need this line at all, right? This means we can just work with this line, right? So we can represent it like this. If I say, so we can just work with this line. 1 is dividing 3 and 3 is dividing 6, so no need to divide 6 with 1 because it's transitive and a partial order relation. So we don't need this. Similarly, you can see that if 1 divides 2 and 2 divides 4, then 1 divides 4. We don't even need this line. Getting my point? Yes or no? So, students, if you look at this line, which is here, we don't even need this line, right? Yes, we won't need this line at all. Is this clear to all of you? Anyway, we will need this. We can't avoid this line because we don't have transitivity here. It's not like 1 divides 2 and 2 is dividing 6, right? If you divide 6 by 1, then it's already connected from here. So, it's understood that we don't need to connect it separately in this. So it's important to note that because of the transitive property, there is no need to create this type of relation. It's understood that it will come by the transitive property. So its hash diagram will be like this. It means that we won't need this line here, which we have. Okay. So we will use the definition of partial order relation to make a hash diagram here at this place. And we remove the unnecessary graphs from here. Is this clear? And we can understand easily which is a minimal graph where there is least representation. We can understand this. 1 is dividing 3, 1 is dividing 2, 1 is dividing 6, 1 is dividing 4, and 1 is dividing 8. You'll see that 2 is dividing 4 and dividing 8 and also dividing 6. Similarly, 3 is dividing 6 and also dividing itself. You can see that 4 is dividing 8 and 8 is not dividing anything. This is the hash diagram and it's very important. If you understand hash diagram properly, then you can understand lattice and all those things easily. Let's see a question. You are asked what will be hash diagram of the subsets of the set S, which includes A, B, and C. It means what will be hash diagram of subsets of set A, B, and C. And ultimately, set of all the subsets that is given to us is the power set, right? If I talk about this set, what are the subsets we can have in this? If we have been given set A, B, C, then what subsets we can have? We can have subsets like phi. Next will be A, another will be B, and next will be C, right? And then students, we will have AB here and we will have BC here, and then students we will have AC here, right? And finally A comma B comma C. The way to write this is to take all elements and raise to the power of 2. So 2 to the power of 3. This means we have 8 subsets here, 1, 2, 3, 4, 5, 6, 7 and 8. Now how do we make a hash diagram of this? Now this hash diagram means we need to take this one into account, the relation we have here. For example, A is its own subset. Yes, A is its own subset. Follow this carefully. This is subset of AB, this is subset of AC, and this is subset of ABC, right? Now, let's see the relation. Now, let's talk about the relation. What's the relation here? Phi will come here. And remember that phi is actually a subset of everything, of A, B, C, and so on. So, we'll write phi with everything, right? Phi will be subset of itself, right? We can write this. So, here we will write phi, right? Then we'll talk about phi. This is the subset of A, right? We will write whose subset is phi. Subset of B. So we'll keep writing like this with all of them. And then students, we'll talk about A. So A is its own subset. We'll write it alone. Now, this A, with whom is this A subset? This A is a subset of AB, right? We can write it like this here. And students, the A that is here, it is subset of which one? It's of AC, right? So students, we can write it like this. Then we know that this A, whose subset is this? And this A is also a subset of ABC. So we can write it here like this, right? And we can write it like this, okay? So we can also write this. Next, we'll talk about B. B is a subset of AB and B is also a subset of BC. Is this clear? B is a subset of both BC and AB. So we can write it like this. But how will we make this in a hash diagram? I want to explain how to make a hash diagram. Try to understand this. So students, in this hash diagram, we will first write phi. Phi is subset of A and also subset of A, B, C and B. Let me explain it to you with a diagram. We should use diagram to explain it. So students, let's try to understand how to make a diagram of this. First, we will write phi. Now listen carefully to me, that phi is subset of which of them? So we will have phi as subset of A. Actually, A5 will come, right? It will come within this. Then we will write B here and we will write C here. So this will be a subset of this and of this also. Getting my point here? And then we know the A that is here. Whose subset it is? It will be subset of AB. So we can write like this here. Now AB is also a subset of B. Now students, here we can write BC. So I will write BC here. Please tell me if I am right or wrong. We know that this is a subset of this and this is also a subset of this. Now students will write A here, since B is also coming into this. It's coming in both of these. B has two branches. Now C will be connected to both because C will be a subset of BC and also of AC. So students, we'll write AC here in the middle. So this will be its subset and this will be its subset. Now, these three will be subset of which one? Students, it will be of A, B and C. So this will go here, this here, and this will go here, right? So students, this will be its hash diagram. So you can easily make a hash diagram like this. This is what you need to pay attention to. Okay, now let's move ahead. And now next, students, before understanding lattice, it's important for us to understand maximal and minimal elements. Okay? What is the maximal element? In a POSET meaning, if we have been given a partial order set in a circumstance, for example, if an element is not related to any other element. If any element is not related to any other element, then we have a maximal element. We call it a maximal element. There's nothing above that. That's what maximal means, that there's nothing above that. And whenever we talk about the hash diagram, the relation is always defined from bottom to top. So, listen, if you see here, 4 is mentioned here. We don't have any element above 4. Ultimately, whatever relation we have, it's always defined upwards. There's nothing above 4. It will become a maximal element. There's nothing above 3. It will become a maximal element. In the same way, there's nothing above 5 here. So 5 will become a maximal element. Understood? In this hash diagram, we have 4, 3 and 5 as the maximal elements, which I showed in the previous example. So, in the last example, the maximal element we have here is ABC. There is nothing above this. Getting it? So, this will be the maximal element. Clear? Let's move ahead. So, what is a minimal element? A minimal element in a POSET is an element where no other element is related to it. That element is what we will call a minimal element. For example, 1 is related to 5, 1 is related to 3, 1 is related to 2, and 2 is related to 4. But nothing is related to 1. There is nothing below 1. There is no element that relates to this one, right? So, this one will be the minimal element. The element with which no other element is being related. This is known as a minimal element. We have discussed this already. What is the upper one doing with the lower element? It relates to it. Imagine the smallest person in a house, right? There's no one to call him big brother. That's what we call a minimal element. Let's understand the diagram again. We have this lattice diagram. So, 5 here is a minimal element. Why is this so? Because nothing is related to it. This is something you have to understand carefully. I hope all is clear now. As I mentioned in the diagram, we have maximal elements which are 4, 3 and 5. And we have a minimal element which is element 1. Maximal and minimal elements. Next, there is a theorem. That theorem states that if we have a finite non-empty POSET, meaning a non-empty partial order set, which we write it like this. Look carefully here. We have a set and we have a relation. It has at least one maximal element and one minimal element. If we have a finite POSET, partial order set, then there will be at least one minimal element and one maximal element. Have you understood? It's understood that if we make a hash diagram, and that hash diagram is finite, it will stop somewhere. And where it stops, that will be the maximal element. This part is basic and already covered. And where it starts, that will be the minimal element. If we have an infinite hash diagram, then we won't be able to find its maximal element. There's no way to know that, right? But if we have a finite POSET and if we draw a hash diagram for that POSET, then we'll have a finite number of maximal elements and a finite number of minimal elements. This is the proof of the theorem. If we take a partial order set, be a finite non-empty POSET, and P1 belongs to as given here to P, and this P1 is not a maximal. If P1 is going to P and P1 is not maximal, then some P2 will exist. Ultimately, we have an element P1 here. Carefully look at this figure on the screen. And if it is not maximal, then there will be something else above it. Only then will it become maximal. If something is not above 5, it will become maximal. Let's say there is a P2 and it will relate to P1 or P1 will relate to P2. Any which way it works, then we will have a line in the hash diagram. This is how it works. Now look at this carefully. So we'll have P2 here where P1 will relate to P2. Now if P2 is not maximal, okay, P2 is not maximal, then what will this mean? Then P3 will be there and P2 will relate to P3. This is all you need to understand. If this keeps happening, then someone will definitely go somewhere and stop, because we have a finite set, a finite non-empty set, and so on. And given that P is finite, so for some element, Pk belongs to P, since there is no element Q of P such that Pk is related to Q. Meaning that we have a particular point where it will stop sometime because it's finite. So let's say it stops at Pk. And what will this Pk do with any one of these elements? Meaning, what will any element do with Pk? It will relate to it. If Pk is finite, so what will this be? It will be its maximal element, right? If there's maximal element and it's finite, then its maximal element will exist. And if it's minimal, then it will have minimal from where it will start. So we need to understand that in this way. We can easily understand this. And similarly, we can use a similar argument for the minimal element. If we have a finite non-empty POSET, then we can understand its minimal element. In this way, if it has a finite POSET, then its minimal element will be at least one element. Okay? Like this, we can easily understand it. Let's move ahead. So look at the next concept. It's lower bound and upper bound. Just like in real analysis, we study upper and lower bound within set, we also have it in the hash diagram. And what is this upper bound? We first understand that if we have any POSET, B is a POSET and B be the subset of P. Okay, B is the subset of P, meaning whatever POSET we have, B is some subset of it. Alright, and if X belongs to A, there is an upper bound of B. But if the X that we have in A, if it will be the upper bound of B, if Y is related to X for every Y belongs to B. Now, what does this mean? I will try to explain it to you through this diagram. So, let's take an example. If someone asks you, what is the upper bound of this 9? So, we have a set named 9. Now, we have to see which element is higher than 9, which is related to it and is also the biggest. Obviously, it's 10. And what will be 10? It will be its upper bound. If you were asked the upper bound of 5, 6, 7, what will be it? So, we can have 9 or even 10 as the upper bound of 5, 6, 7. We will have to. Now you will say that sir 4 and 8 can be, but my dear, they are below that because the relation is always upwards. Getting my point? So here 9 and 10 will be our upper bound. If you are asked what is the upper bound of 3, so the upper bound of 3 can either be 5 or 6 or 7 or 9 or 10. Getting my point? Now sometimes in exams, you are asked about what are least upper bound. For example, of 5, 6, 7. We have two upper bounds. One is 10 and other is 9. If you were asked what is the least upper bound, then it will be 9. Is this part clear to you? So, the upper bound means that whatever is our hash diagram to which it's connected, where it's making a relation. Understood? So, you have to see there's an element just above it. That element is just above it, and what is it doing? It's relating to it. So, what will happen to that? It will become upper bound. That's what it's saying in this definition. Now, we will talk about lower bound. An element X belongs to A is lower bound of B. If X is related to Y for every Y that belongs to B. If I tell you what is the lower bound of 5, 6 and 7. So, its lower bound will be 3, 2 as well as 1. There will be 3 lower bound, right? They all are coming where? Below it and are also relating with it. If you are asked what is the greatest lower bound, which one is the biggest among 1, 2 and 3? 3 is the biggest. So, what will we get? It will be the greatest lower bound. If we talk about how much lower bound of 9 will we have? So, we'll have 4, 5, 6, 7, 8 and even 1, 3 and 2 as lower bound of 9. All the elements that are below it and are relating to it, what will they be? They will be its lower bound, right? We can easily understand like this. If we have 10, then everything below it will be our lower bound. This is what we need to pay attention to. Let's move ahead. So students, now we will talk about lattice, and if we have been given any, POSET meaning any partial order set is said to be a lattice if every two elements in the set L has a unique least upper bound and unique greatest lower bound, right? Now we will try to understand its definition. In this video, I am trying to tell you what does every two elements mean. We have 5, 6 and 7. We took 3 elements. So what will be the upper bound of these 3 elements? You said 10 and 9 will be its upper bound. Then I asked what would be the least upper bound, and you said it would be 9. That is why I said it in front of you that lower bound of 5, 6 and 7 will be 1, 3 and 2. And when I asked about its greatest lower bound, then you said it will be 3. But when we talk about lattice, then we won't take 3 elements. We will take only 2 elements at a time. Either take 5 and 6 or 6 and 7 or 5 and 7. Take any 2 elements, okay? In an arbitrary set, take any 2 elements and the least upper bound or greatest lower bound of those 2 elements should exist here, and it must also be unique. If this happens, then it's called lattice. And this is its definition. Here we are taking 3 elements, but we just need to take 2 and our work will be done. Let's try to understand example. So, for these 2 diagrams, we will see that which is our lattice. So, For the definition of lattice, we must have an unique least upper bound or the greatest lower bound, which should also be unique. First of all, I will try to make you understand this diagram. Suppose we took two elements, f and g. We will see its lower bounds, that which are the lower bounds. Then we'll talk about greatest lower bound. So let's see if b is lower bound of these two. So see, b is relating to f, but b is not relating to g. It should relate to both. Then only it will become a lower bound. Is it clear? Similarly, c is relating to f, but it's not relating to g. So this too is impossible. So now we'll talk about d, which is relating to g, but it is not relating to f. So this can't be lower bound either. So students, this e is relating to g, but e is not relating to f. So this won't be a lower bound. Now let's talk about a. A is relating to f and a is also relating to g. And this is the only one. So what will be this for us? It will be its greatest lower bound, which is unique as well. Now we will talk about its upper bound, that whether we have one or more than one least upper bound. Is it clear? So now we will talk about upper bound through this diagram. Now students, we will talk about upper bound. We will firstly talk about f, which can be the upper bounds for f, meaning f is relating to which other elements. So f is relating to I and f is also relating to h. It is relating to k as well as to j. It is relating to all the four elements. Correct or not? Similarly, we will talk about g. G is relating to h. G is relating to j and it is also relating to I and k. These four will be its upper bound. Now that we have the upper bound with us, we will talk about what will be its least upper bound. The least, as we have both of them just above it, so least will be these two, h and I. Then I will remove one above because while taking least, we remove the one above. So students, h and I will be its least upper bound because f is relating to h and even g is also relating to h and both are on the same level. So both of them will be the least upper bound. But the least upper bound which we have, it is not unique. And when it is not unique, then it means that we do not have lattice. This we should keep in mind because whatever is our unique upper bound, it should be unique for at least two elements, right? And what should be its greatest lower bound? So its greatest lower bound is unique. But our least upper bound is not unique. That is why this is not lattice. Now we will talk about this diagram. So for this diagram, let's select any two elements. I will take E and G elements. Take any two. E and G, or if you want, you can take B and D as well. As you wish, right? Now we will talk about E and G, but here we are getting only one upper bound, that is H. And this is the only least upper bound we have. So what will be its unique? It will be least upper bound. Now students, we will talk about its what? About its lower bound. So which can be the lower bounds of E? Well, the lower bound of E can be either A or B or C or D. We can have four lower bounds. But one thing that we need to keep in mind is that B is relating to E, but B is not relating to G. So it cannot be a lower bound. Why? Because it should relate to both of them. Similarly, we will talk about D. D is relating to G, but it is not relating to E. So this cannot be a lower bound either. Now C is relating to E and C is relating to G as well. Also A is relating to E and A is also relating to G. So the lower bound here will be C and A. Here it's asking what will be its greatest lower bound. So in the greatest lower bound among C or A, the one above will be our greatest lower bound. And C here will be the greatest lower bound of E or G. And this here is unique. It means that it will be our lattice. So in this way, we can understand it very easily. Now, let's try to understand another example. Let S be non-empty finite set. P S be its power set. And we have to find its power set and show that this is lattice. When I told you about hash diagram in example, there I had told you how to draw hash diagram. Here we take two elements. And what could be the power set of two elements here? For two elements, it can be phi A, B and AB. If we make its diagram, then phi is a subset of A as well as B. And A is the subset of AB. We can easily understand in hash diagram. Now, we have to check whether there is a lattice in this hash diagram or not. So, we have to check the greatest lower bound and the least upper bound to see if they are unique or not. So, first of all, we will take two elements A and B. As you can see, we have only one element above it, which is AB, which is its upper bound. And then what will happen? This will be its least upper bound. So students, now we will talk about phi. What is phi here, my dear students? Our phi here is single and we have its lower bound as well as its greatest lower bound. So this is also unique. Hence, this will be the lattice. So like this, it is very easy. Or you can take these two as well or these two. Now you will think, why can't we take these two? Then you can take these two or you can take these two and easily understand as well. You can easily understand that here. Suppose you take these two here and if you have to find out what its upper bound is, then this can be its upper bound. So let's talk about if you are thinking that what will be the greatest lower bound and least upper bound of AB and B. So if we take AB and B, then the upper bound that we will here will be AB, right? And that will be the least upper bound here, right? Is it clear? And if we talk about what will be its lower bound, then if we talk about its lower bound, then we will get phi. And if we talk about greatest lower bound, then we also have greatest lower bound, which is phi. So you can take any of these two. It will be very easy to prove that we will have a lattice. Is it clear? So we can understand it like this. Let's try to understand another example. Let L be the set of all factors of 12. What does it mean? It means that if we take its set of all that are the factors of 12, and this arrow denotes the divisibility relation, right? That the element which will divide it, okay, will relate with it too, right? Then show that this relation is a lattice. You have to show that this relation is lattice. So what factors can we have of 12? We have all the factors of 12. What could they be? 1, 2, 3, 4, 6 and 12. Now we will define its relation. You can make a relation that 1 divided 1, 2 and 3, right? You can make it like this. 1 divides 1, 1 divides 2, 1 divides 4, 1 divides 3, 1 divides 6. We can draw a hash diagram. Now we'll talk about 2. So what is 2 dividing? 2 divides 6, 4 and 12. If we talk about 3, 3 divides 6 and 3 divides 12. Similarly, we will talk about 4. So 4 divides 12 and none other. While 12 divides 12, so what do we have here? We have a hash diagram. Now let's see here, we will take any two elements and we will find if its least upper bound and the greatest lower bound are unique or not. So let's say I have taken 6 and 2 here. Let's take 6 and 2, then its upper bound will be 12 and 4 is also possible, but 4 is not related to 6 here. So we will have only 12, which will be its upper bound. And what will happen to it? It will be our least upper bound. If we talk about the lower bound of 2 and 6, then lower bound will be 1. It can't be 3 because it's not relating to 2. We'll have this and this is also unique. We'll have this lattice. If you want to take 2 and 3, then you can take it. If you take 2 and 3, then in this case, its upper bound could be 6 and 12. It can't be 4 because 4 is not related to 3. So students, we will talk about which will be the least upper bound of 6 and 12. It will be 6, which is unique. Now about the lower bound of 3 and 2. So the lower bound is coming 1, which is unique. So if you take any two elements, then the least upper bound and the greatest lower bound will be unique. What will it be? It will be unique. That means this diagram will become a lattice. So in this way, we can easily find out. Have you understood? It's pretty simple. Let's take another example. A is equal to 2, 3, 4, 6, and this be the divisibility relation on A. There's a divisibility relation. So you have to know that this A divisibility relation is POSET, not lattice. It is POSET, but it won't be lattice. You have to find out that either its least upper bound won't be unique or its greatest lower bound won't be unique. This is to keep in mind. So what will we do? First, we will draw a diagram. I will draw a diagram. See here. So students, what all is 2 dividing? Let's focus on 2 first. It is dividing 4 and 6. Okay. So I will write 4 here and I will write 6 here. So 2 is dividing this, 2 is dividing this. Clear? But 2 is not dividing 3. Now we will take 3. So students, 3 is dividing what? Okay, so it is only dividing 6 and it won't divide anything else. So this will be its hash diagram. Now this is the hash diagram. We can divide it like this. And there's no need of telling that it can't be divided by itself. And 3 doesn't divide, 6 or 4. Then it won't be connected. So now we will talk about any two elements and find out their upper bound. And then we will talk about its least upper bound. So let's look at this diagram and understand it. Assume any two elements, 3 and 4. I will take 3 and 4 and find out about its upper bound here. Okay. What is its upper bound? Then we will talk about what its least upper bound actually is. So we will see that the possibility of its upper bound seems to be number 6. But here you can see 3 is relating to 6, but 4 is not relating to 6. So 6 can't be the upper bound of 4. Clear? So the upper bound of these two does not exist. So see, to have an upper bound, it's necessary that they relate. Meaning 4 should divide 6, but it's not. There is no connection between them. It means there is no upper bound of any of the two elements. Then this lattice will not be formed. Are you getting it or not? This is what we need to pay attention to. If you wish to know the lower bound, then we can take their lower bound. If we take lower bound of 3 and 4, then only 2 is the possibility. Or take the itself one. But there is no use of taking those because ultimately, when we don't have a smaller element left than 3 or 4, then we talk about the itself ones, right? 2 is existing here because 4 is relating with 2 here. Getting my point? But 2 is not dividing 3 here. So what will 2 be here? It will not be our lower bound. So students, we won't even have the greatest lower bound. So neither we are getting the least upper bound nor the greatest lower bound, which means that we don't have the lattice. So I want to tell you that whenever we talk about lattices, the diagram should be closed. There is a possibility in closed that it becomes our lattice. This is not a closed diagram. It's an open diagram. That's why there's no chance of it being a lattice, right? This is how we can understand it. Thank you so much for watching. Please tell me how did you like the video by commenting below. You can watch my Discrete Mathematics playlist at the end. You can go check out our new channel where we are uploading many videos, where we are sharing many tricks, and you can subscribe that channel here. Thank you so much. Bye-bye. And do comment. Thank you.